Welcome to this explainer. Today, we're going to dive into the meticulously structured and honestly, surprisingly fascinating science of exactly how we measure the invisible ingredients in everyday construction. When we look at a towering skyscraper or a massive highway bridge, we tend to just see solid, immovable rock, right? But behind every single successful pour of concrete is an incredibly rigorous set of tests happening right there on the job site. Specifically, we're going to look at the Canadian standard, CSA A23.2-4C. This outlines the pressure method for testing plastic concrete. So let's dive into this and decode the blueprint of absolute structural integrity.
So before we break out the heavy machinery, I want you to think about this. What is the invisible ingredient that dictates whether a massive structure will stand the test of time, withstand freezing winters, or, just completely crumble under pressure? It's not the cement, it's not the gravel, it's actually air. Yep, entrained air bubbles are intentionally mixed right into concrete to give it durability, especially against freezing and thawing. But here's the catch. If you have too much air, the concrete loses its strength. Too little, and it cracks under environmental stress. This test is all about finding out exactly how much air is hiding inside that mix. Now, the standard specifically refers to testing plastic concrete. Let's clear up that engineering jargon right off the bat. We aren't talking about synthetic polymers or plastic bags here. In the construction world, plastic concrete simply means fresh, workable concrete before it hardens. Think of it as the raw, workable dough of the construction world that just hasn't baked yet. The standard tells us that measuring the air content in this plastic state is absolutely crucial, but it also notes that the air content can actually change once it hardens due to things like environmental exposure, how it's delivered, or even how it's pumped. Here is the architectural blueprint for today's explainer. First, we'll cover the hidden bubbles. Next, the testing toolkit. Then the 10-minute race, calibration, under pressure, and finally, grading the pour. Let's start with Section 1, the hidden bubbles. So how exactly do you measure something you literally can't see that's trapped inside a dense, gray mixture of rock and paste? Well, it relies on what's called the pressure method. The core mechanism here is remarkably elegant. Basically, it involves applying air pressure to a known volume of concrete to compress the entrained air inside its pore structure. Think of it kind of like a specialized pressure cooker. By filling a rigid bowl with concrete, sealing it tight, and injecting a known amount of air pressure, we can observe the drop in pressure, and that drop correlates directly to how much air was squeezed inside the concrete. It is worth noting, the standard does mention this specific method isn't really suitable for highly porous aggregates, but for standard concrete, it's the absolute gold standard.
Moving right along to Section 2, the testing toolkit.
You can't perform a test of this magnitude with just a bucket and a stick. What is truly fascinating here is the sheer specificity of the tools required by the standard to get this high-stakes job done right. First, we need a pressure-tight measuring bowl and cover assembly that absolutely won't expand under force. But look at the tactile instruments. A technician must use a round, straight steel tamping rod exactly 16 millimeters in diameter with a hemispherical tip. If they use a vibrator, it has to operate at exactly 120 hertz internally or 60 hertz externally. And my personal favorite, a rubber or rawhide mallet weighing exactly 0.6 kilograms, give or take 0.3. This isn't just a random list of items, it's a precisely calibrated orchestra of physical tools designed to manipulate the concrete dough with exact, repeatable force. It's pretty wild how microscopic details dictate our macroscopic tools. The capacity of the measuring bowl you use entirely depends on the nominal maximum size of the coarse aggregate, basically the rocks in the concrete. If your rocks are 40 millimeters or smaller, you use a 7-liter bowl. But if they're up to 56 millimeters, you actually have to bump up to a 15-liter bowl. Every single variable is accounted for, making sure the sample is truly representative of the overall batch.
All right, Section 3, the 10-minute race.
Because in construction, time is quite literally solidifying. 10 minutes. That is the strict, critical time constraint mandated by the standard. From the exact moment the sample is obtained, the technician has exactly 10 minutes to complete the test for air content. And get this, that includes transportation and remixing the sample. It injects this crazy ticking clock urgency into the whole procedure. You can't just take a sample, go grab a coffee, and test it later. No way. The concrete is a living chemical reaction, and its plastic state is incredibly fleeting. Which brings us to Section 4. Calibration. Since time is of the essence, we really have to prepare beforehand. Before the concrete even arrives on site, the equipment must be perfectly tuned. The standard outlines this rigorous calibration process, usually using water. You fill the measuring bowl with water, clamp the cover, and use a syringe to expel every single drop of remaining air out of the petcox. Then, with the valves closed, you pump air into the chamber slightly past the starting point, carefully bleed it back to the exact initial line, and open the operating valve. The gauge should read exactly 0%. This establishes our absolute baseline. Honestly, if a meter with just water in it reads anything other than 0, your entire foundation of data is flawed before you even begin.
Now for the heavy lifting. Section 5, under pressure.
With our instruments calibrated and the clock ticking, we move to the most physical and action-packed part of the standard. The crucial point here is how we actually get the concrete into the bowl without accidentally trapping extra unwanted air. The standard divides this into two distinct methods based on the slump, which is essentially how wet and flowable the concrete is. If the slump is greater than 40 millimeters, you use the rodding method. You fill the bowl in 3 equal layers, driving the tamping rod in 25 to 50 times per layer, and tapping the sides 10 or more times with that highly specific rubber mallet to close up the voids. But if the concrete is stiffer, with a slump of 40 millimeters or less, you vibrate it in just 2 layers, inserting the vibrator 3 times per layer. The physical labor here is intense but highly controlled, because as the standard explicitly warns, over-vibrating can actually cause you to lose the intentionally entrained air. Once consolidated, we must perform the strike-off. You take that steel strike-off bar and finish the top surface so it's perfectly smooth. The standard is incredibly specific here too. An excess of concrete protruding approximately 3 millimeters above the top is considered optimum before striking it off. The entire goal is to leave the measure perfectly level and meticulously cleaned off on the exterior. It has to be perfectly flush, ready for the lid, so the volume is absolute. It's actually a really satisfying step.
And now, the climax of the test. You clamp the cover on and inject water to expel any ambient air lingering just above the concrete. You pump the air chamber up to the starting point. Then you open the main valve, releasing the pressurized air down into the concrete bowl. And here is a fantastic phrase straight from the standard. You must strike the bowl smartly with the mallet. This physical jarring ensures the air pressure fully normalizes through that dense mixture. After the needle settles, the technician reads the air percentage on the dial, recording it to the closest 0.1%.
Let's wrap up with Section 6, grading the pour.
So how does all this tactile, physical labor translate into a permanent legal record? Well, the reporting requirements are incredibly strict. You have to document the source, the exact date and time, and precisely where this specific batch of concrete was poured into the structure under construction. It demands the identification of the certified lab, the name of the technician who performed the test, the air content down to the 0.1%, and the signature of a reviewer. This ensures absolute traced accountability for every single batch of concrete supporting our bridges and skyscrapers. It's a huge deal. I want to end with this fascinating, honestly, almost philosophical statement directly from the precision and bias section of the standard itself. It states, this test method has no bias because the air content of freshly mixed concrete can only be defined in terms of the test methods. Think about that for a second. The test is so fundamental to the material that engineering objectivity is literally defined by the very procedure we just performed. There is no true air content out there floating in the universe to compare it against. The reality of the material is defined by the precise swing of a 0.6 kilogram mallet and a perfectly sealed bowl. What other invisible realities in our built world are entirely defined by the way we choose to measure them? It's definitely something incredible to ponder the next time you walk past a construction site. Thanks so much for joining me on this explainer, and keep questioning what holds your world together.